Okay. Okay. Isn't the Lie algebra okay? And we have the following definition. So for any x in G, we, we consider the nil space is a union of the kernels of the power of ADX, and say X is regular if the dimension equals takes the smallest possible value. And so this minimal value, we will call it the nilpotent rank of G. Okay, and we have the following proposition. So let X be an element of G and set H equal to the nil space. Then we have the two properties that firstly, H is a Lie subalgebra. Furthermore, H is its own normalizer. So this is, it is equal to the set of those Y's such that add Y of H is contained in H. And also, if we consider the map induced by ADX, well, so when we have proved that this is, well, so of course, X is an element in there because, and so once we have proved that H is a Lie subalgebra, we know that add H takes H into H, so it induces a map, an endomorphism of the quotient space. And the claim is that this map is injective. Okay, and this is the second statement of the proposition is that if X is regular, then H is nilpotent. Okay, in this case, we say so the nil space of a regular element is called Grothendieck-Cartan subalgebra. Okay, so let's prove this. Okay, so set let's denote by capital D the endomorph at X. Then H is a set of those Y such that there exists N such that dn, d to the n of Y is equal to 0. And so if we have two elements in H, then the Lie bracket is again in H by a Leibniz formula. Because this ADX it's a derivation of the Lie algebra. So that is, if we apply dn to a Lie bracket, this is a sum for I equals 0 to n of ni di of y bracket of z. And so this is 0 if n is larger, because since y is in H, we can pick. So this is 0 is if I is large enough, and this is 0 if n minus 1. And so for n large enough, at least one of the two is 0. So this is truly a Lie subalgebra. And now let's Y in J such that as Y of H is contained in H. Then, in particular, then the bracket of Yx, which is equal also to minus H. And there exists n such that dn d of y is 0, hence y is in H. Okay, so the normalizer of H in G is no larger than H. And so this also proves the second statement. Because if so this shows that if d of y is in H, then H already is in H. And so this means that the action of D on G over H is injective. Okay, so we have this statement. And we have to prove now the more difficult second statement. So assume X is regular. So we want to prove that for any y in H, this guy is important. Because by Engel's theorem, this H is important. And it suffices to check that all derivations are unimportant. And so we can extend K to its algebraic closure. And so we can assume K is algebraically closed. And so we know already. So we know that this one is injective. And therefore, there exists U, an open dense subset of H such that for any y in this one point in this one, this one is injective. Because by definition, so this is a condition that some determinant is non-zero. So the set of those y satisfying this property is an open subset in any case, and it is non-empty. So it contains X, and set is non-empty, and therefore dense because well, H is a vector space. And so this says that for any such point, this tells us that the nil space of Y in J is contained in H because on the quotient vector space G over H, 0 is not an eigenvalue. So the nil space is entirely contained in H. But H is also this. And this one has minimal dimension. So actually, for all such Y, we have this equality. So this nil space is H, which is this. And so if we denote by R the dimension of H, and consider the map from H cross H to H, which sends an element X and Z, YZ to add Y of Z. So this is 0 on this U of K cross H. Okay, because Okay, because for any such, for any y, so this tells us that y is nilpotent on H, and H has dimension R, and we know that an nilpotent homomorphism in an R-dimensional vector space, then its R's power is zero. So this map is identically zero on this, and so this is dense. Hence, it is zero on H cross H. And this proves that H is nilpotent. So this proves that H is nilpotent. Because then any element Y in H acts nilpotently on the Lie algebra. Okay, so we have this this proposition, and so now we have at our disposal as those G-Cartan subalgebras, which are nilpotent subalgebras equal to their own normalizer. Okay, so let us prove. Let us prove somewhere. Okay, so I will erase this. And I just want to write about an easy proposition that we will need later. So we have the easy proposition. Oh, by the way, yes, so this was numbered 29.5, I think. No, this was 0.3, because there must have been some remarks to that. And there is an easy proposition with numbering 29.6. So let X in G be regular and H a Lie subalgebra such that X belong to H. Then firstly, we have that H is nilpotent. If and only if H is contained in the nil space. And secondly, as a nil space is the unique G-Cartan subalgebra containing okay. So the proof is very easy. So in one, so this implication is obvious because since X is regular, we have seen that this one is nilpotent. So if H is contained at one, and the other is easy because if X is in J, which is a nilpotent Lie algebra, then add X on H is nilpotent, hence H is contained in the nil space. Okay, so if X is in H, which is a nilpotent Lie algebra, then this one is nilpotent because the Lie algebra is nilpotent. And so this gives that H is contained in the nil space. And so this implies too that if X is contained in some other G carton, with X prime regular. So this one is important. Hence, by the previous implication, we have the inclusion but they have the same dimension, but both have dimension. They have the same dimension, which is the nilpotent rank of G, and they are equal. Okay, so this is reminiscent of the fact that if you take a regular element in a maximal torus, it is contained in a unique maximal torus. And so this is a Lie algebra version of this. Okay, and now the key theorem is the following. Key theorem. Oops. Okay. So now let G be a smooth. I think I want what? Let's write connected just to be safe. Connected, smooth, affine J group, and let G be the Lie algebra. And let's consider a Cartan subalgebra. With X regular. Okay, so this exists, and we have the two statements that we will prove later. So firstly, there exists a unique, smooth, connected, closed K subgroup H of G such that E of H is equal to H. So Cartan subalgebras come from subgroups, and if we take a larger field with K algebraically closed with transcendence degree of K over the prime field bigger than the dimension of H, then it's easy to see that HK contains a maximal torus of GK. Okay, so let's assume this for the moment. And using this, let us prove that G contains a maximal torus. So this is a key technical point, and we will prove it afterwards. So taking this for granted, let's go into section 30, which is existence of a maximal. Yep. Mm-hmm. No, 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 no. No, no, not at all. Uh, uh, no, no, but in fact, it will be abelian. In the reductive case, it will be the Lie algebra of a torus, and it will be abelian. Uh, Basically, the fact that it is nilpotent is used in this uniqueness statement. The important point is that a regular point is contained in only one G-Cartan subalgebra. Yeah, yeah, you're right. That's another thing. So this statement is important because this will be used to prove that some map is dominant and generically finite. And so this is the trick. No, but yeah, you are anticipating something which is coming. So existence of a maximal torus in G. Okay, so from now on, the standing assumption is that G is connected smooth over K. So let's start with a proposition. So suppose reductive center of G is trivial if G is nilpotent, then the trivial group is a maximal torus G. Okay, so this is one extreme case, and then we do the general case. Okay, so proof. Okay, so, and from now on, so K will denote an algebraically closed large enough. Algebraically closed field large enough. So we just pick, so let's PK be a maximal torus in GK. And let us denote by frac T, the Lie algebra. So we are going to prove, that the Lie algebra is 0. Hence, hence the trivial group is a maximal torus in GK, hence also in G. Okay, so it's enough to prove that this Lie algebra is 0, because this will say that, there is no torus at all in GK, and therefore the trivial group is already a maximal torus in the beginning. Okay, so consider, yes. Yes. So this proves that there are no tori at all, because any tori is contained in the maximum torus. No, but K is algebraically closed. Yeah. K is algebraically closed, and then we use the classical theory. Okay, so consider the restriction to T. Well, yeah, here I don't need a subscript, so it is a maximal tori in there. So consider the restriction to T of the adjoint action. Then we saw the other day, we saw that so the other day I called it theta, so it is the restriction to T of the adjoint representation. And so we saw that the kernel of theta is a reductive center for GK. Hence, it is a trivial group, because by assumption, the reductive center of G is trivial, and reductive center is preserved by base change. Hence, theta is a closed immersion. So it's a monomorphism. And it's even a closed immersion. Because we saw in August in some lectures that a monomorphism with source, a group of multiplicative type is always a closed immersion. And so this tells us that the map from T to the endomorphism of G, so this map is also injective. Because it's a derivative of a closed immersion. Well, so here we are over GK. Okay. Okay, but T acts semi-simply on GK. And in fact, the GK is equal to so we have the usual decomposition. And so this means that T acts semi-simply. Also, because it just acts by the derivative of the character. But G is nilpotent, and so GK is also nilpotent. And T acts, well, nilpotently. And because, well, since the whole algebra is nilpotent, then this subalgebra has to act nilpotently. And so each element out of an element of T is both semi-simple and nilpotent. And so we obtain that the adjoint action of T is 0. And so this map here, this is add. But since this was injective, this gives that T is 0. Okay, so we have this argument which treats this case that you cannot have both trivial reductive center and the Lie algebra being, well, if we have both of these, then there are no torus. So we are fine. And now we can proceed with the proof. . And hmm? Yeah, exactly. Yeah. And now we have the theorem. So the first assertion is that G contains maximal torus. And more precise statement that if G is semi-simple adjoint of adjoint type, then every G-Cartan subalgebra of G equals is the Lie algebra of a maximal torus. Okay. Ah, yes. So we prove A by induction on the dimension of G. So it's okay on the okay if on so let's call n the dimension of G. Okay. So so of course if n is zero, G is a trivial group and there is nothing to prove. So we can assume n strictly positive and the theorem proved for all dimension strictly smaller than n. Okay, and so let H be a G-Cartan subalgebra with X and G regular. And so by the theorem, which is still there, we have that H is equal to the Lie algebra of some subgroup with H connected smooth closed subgroup such that HK contains a maximal torus of GK. Okay. So there are two cases. So first case. Oh, okay. No. So there is a first reduction. So let Z be the reductive center. So we can replace G by the quotient. Hence, we can assume that the reductive center of G is trivial. I mean, it suffices to prove that this one contains a maximal torus, because then the inverse image of this of the maximal torus, etc. So we work with this one, and this we call G again. So we have this assumption. And now there are two cases. So the first case, and okay, so I should have all this as I should have said before. Okay, so this is the first thing that we do. So this comes, okay. So this comes here. Okay, so we first reduce to the case where the reductive center is trivial, and then we obtain this subgroup H. Now there are two cases. The first case is that if the dimension of H is the dimension of G, then since G is smooth connected, then G is equal to H, and L of G is equal to L of H, which is important. Because L of H is this Cartan subalgebra, which is important. So this answers your previous question. And so now we have a group with trivial reductive center and nilpotent Lie algebra. And so the proposition imply in this case that the trivial group is a maximal torus of G. Okay, so we are done in this case. And the second case, well, the dimension of H is strictly smaller than G. And then by the inductive hypothesis, H contains a maximal torus T of itself. But then Tk is a maximal torus of Hk, which contains a maximal torus T prime of Gk. And so we obtain that the dimension of T is and so we obtain that this T is not only a maximal torus in the subgroup, but it's a maximal subgroup. It's a maximal torus in G. Okay, so that's a wonderful proof. We don't really understand what's going on, but the proof works because so it looks cheating somewhere, but well. So we have this first case, the dimension does not decrease, and we are good. And otherwise, it works. Okay, so this proves this. So this proves this. And now let us prove this more precise statement. Okay, so we can get rid of this. And let's prove the second one. So second assertion, so assume G semi-simple adjoint. Let H appear as in A, that is connected smooth and the Lie algebra is a G carton. Algebra. Hence, as minimal dimension among those possible. And we know that HK contains some TK, which is a maximal. Okay, so we just proved. So we proved that H contains T, which is a maximal torus of G. And we want to prove that they are equal. So it's enough to prove that they have the same dimension. But now TK is a maximal torus of GK. And we have the usual decomposition. So this is Lie of TK plus the sum. Okay, and now since G is adjoint, okay, so R is a root system of this, and let delta be a basis of R. So we just take a set of simple roots, and since G is of adjoint type, so this implies that delta is a vector space basis of, okay, so this Lie algebra, let me denote it by frac T. And so this, the simple root form a vector space basis of the dual of the carton, because which is the character group of the tori tensor over Z with K. Okay, because we know that for group of adjoint type, a set of simple roots form a basis of the character lattice. So we have this, and each alpha in delta is non-zero linear form on because each is part of the basis, so each is non-zero. And since any root is obtained from the simple one by the action of the Weyl group, each root is non-zero. Hmm? Yeah, you're right. As an element of this space. Okay, and so all the roots are non-zero a non-zero linear form, and therefore we can pick let H let small t be an element in TK, which is not in the kernel. Okay, so we have finitely many hyperplanes, and our field is infinite, so we can pick a regular element. And then we see that the nil space of TG is exactly the Lie algebra of the torus, because T is acting via a non-zero scalar on this. Yeah, the zero eigenspace. Yeah, So it's even the kernel of T. But it's also the general eigenspace. And so this okay, so we obtain that the dimension of our torus, so the dimension of T is equal to the dimension of this Lie algebra. And so this is greater than the dimension of H, because H, by definition, this assumes the smallest possible value. Okay, and so this is the dimension of H. And since we had this inclusion, we obtain this. Okay, so this works. Hmm? Yeah, this is Grothendieck proof. And so you see that this works perfectly, but remember that in the proof, okay, so the proof now is finished. But let me make the following remark. So in the proof, it was crucial to go from G to the quotient group with trivial reductive center. And this is really crucial because so this proves that so this proof of Grothendieck, which works in the semi-simple So in the semi-simple adjoint case, we have a good correspondence that the Cartan subalgebras in the Lie algebra are really the Lie algebra of the maximal torus. But so this fails for SL2 over a field of characteristic 2 because Lie of SL2 over a field K, because so if we take the standard basis of SL2, so the Lie brackets is this. Oops. Okay, because so we see that in characteristic 2, the Lie algebra SL2 becomes an nilpotent Heisenberg algebra with two generators X, Y, and the bracket is central. So it is nilpotent. And of course, I didn't say it, but in a nilpotent a nilpotent in a nilpotent Lie algebra is a Cartan subalgebra of itself. So for SL2, that does not work because the Cartan subalgebra is a whole Lie algebra, and we get the group SL2 itself instead of going down to a maximal torus. Okay, so this is because here's the root alpha. In this case, the root is equal to twice another element in the weight lattice, and so the root becomes 0. It is a 0 linear form, but this does not occur in the groups of adjoint type. Okay, so all this business about reductive center and modding out by the reductive center, it's crucially used in that proof. Okay. Okay, so let me take maybe 10 or 15 minutes more to just to begin the proof of this. Maybe I can prove the first assertion, and I will continue with the second assertion next time. Okay. Okay, so let's start the proof of this key theorem, at least the first part of it. So by the result, actually it has number 26.4 in lecture 11. So this is a lecture I didn't make yet because I gave you the text of this lecture, but I didn't make it already because it's about technical result, about representability of some functors. So by some technical result from this lecture, the group functor So the normalizer in G of H. So this functor is defined analogously to centralizers, is represented by a closed subgroup scheme N of G. Okay, so we have some group, and and let us write. Okay, so and now let's consider the morphisms. So G cross H going to G. So this is the morphism which sends oh, sorry. So we have this morphism. So I regard H as a scheme. So it's a vector space. So it's a K scheme. And so we have this this morphism, and so this group N acts freely on the right of this by what you think, that is G comma H acted on by N. It is Gn and adjoint action of N inverse of H. Okay, and so let's call phi this morphism, and so the action is made so that phi is invariant under this action, and so we are over a field and we have a free action. So you believe me that the quotient exists, and so we make the quotient by this free action, and so we denote by the usual notation for the quotient, and we call this. So we denote by Q the quotient map, and as I said, so this map, so 5 factors through a map psi that goes from X to. Hmm? Well, no, it's SGA, it's expose 5 of SGA, which shows that over a field, quotients always exist. Yeah, so for the existence of quotients over a field, so this is quotients over a base field. And so this is also, so this is also contained in the book by De Mazur Gabriel. Okay, so yeah, so just to play safe, yeah. So the case of a field was treated in the first volume of SGA3, so we know that we can do this. Okay. And I remind you that I proved an easy proposition. So we know that H, which is a niche space, is the unique G-Cartan subalgebra containing X. Okay, for X regular. And so what does this tells us that what is the fiber of psi? What is the fiber of psi over X? Well, so X is in the image of well, yeah, if X is in the image of this couple, this means that X belongs to the conjugate of H by G. And if we go to the quotient, so well, so okay, so this is a fiber bundle of a G over N, and N is a normalizer of H. So actually, so this is a set of conjugates of H, and the fiber is H. So okay, and so since X is contained in a unique conjugate, it comes from a unique point here, and in the fiber, it's X itself. So this means that the inverse image is actually the image by the quotient map of the unit element on X itself. And so this tells us that so there is one fiber which has one element, so phi is generically finite. And so this says that the dimension of the source is smaller or equal to the dimension of G. Okay, so that's one thing. And now, what is the tangent? Let us compute the tangent map to phi at the point E and X. So this map, let's call it d phi. So it goes from G cross H to G, and it sends an element, a couple YT. So if we make the computation correctly, it goes to T plus the bracket X. So for this X, for this X here. And yep. And so it will be surjective. If the map induced by ADX on G over H is, because here we have freedom to, okay, so if, well, if we pick an element of G, so we have freedom, we can choose the part in H, and so it's enough to say that this one is, which is the case if ADX G over H is injective. But this we proved. We proved that for a regular element, the adjoint action on the quotient is injective. And so this one is surjective, and so this one is, and so phi is smooth at the point EX. Hence, phi and psi are dominant. Okay, it is smooth, so the image contains an open subset near the image here. And since phi factors through this one, so this means that phi is dominant. Okay, and so this tells us that the dimension of the source is greater than the dimension of G, and hence we have equality. Hence, the dimension of G is equal to the dimension of X, which is the dimension of G minus the dimension of N plus the dimension of H. And so since G is smooth, so this is the dimension of the Lie algebra. And so we get that the dimension of N is equal to the dimension of H. Okay, and now we are nearly finished. Because N was defined as the normalizer in G of H. And so this tells us that the Lie algebra of N is contained in the normalizer in G of H. Okay, if we take an element that normalize H, then it's the Lie algebra normalizes. But we knew that this is H itself. Okay, and okay, so we have this, and the dimension of N is a dimension of H, and so this implies that N is smooth, and the Lie algebra is H. And now the H, of course, we take H is equal to the connected component. So this one is smooth, connected, and Lie of H is equal to H. Okay, so I haven't proved uniqueness. I will do this next time, but at least I've proved that we can integrate a J-Cartan subalgebra to a smooth connected subgroup. Okay, so uniqueness is easy. Well, if you have two smooth connected subgroup with the same, okay, and now there is another beautiful argument for the point two, so that we will see next time. Okay, so